Doing this. Cool. And yeah, if there's any comments in the chat too, I probably will not see those. So please, again, just call out if you have any questions for me. And for people that come in late, if they start posting questions in the chat, please, one of you all redirect them to speak out loud. Thank you so much. Okay, cool. Okay, once again, confirming, can y'all see exam two review in this PowerPoint?
Yes.
Yay. Thank you so much. Okay, let's get right into it. Exam two is considerably more mathy than exam one was. It's just a consequence of us like moving past the more simplistic, like this is an atom, this is a molecule. And we're now actually going to be able to apply some chemical concepts. We're going to figure out the stoichiometry of things. In other words, how much of this is necessary for how much of that. These problems are not in any particular order, but I have tried to grab at least one of each type of question that wasn't just pure knowledge base. There are a few like multiple choice things on the exam that I'm not putting here because then I would just spoil what the question is. Make sure that you have like a basic understanding of each of the different readings. Make sure you know how to do reaction types, solubility tables, stuff like that. Let's start off with our bread and butter over here, balancing a chemical reaction. It sometimes helps to identify what type of chemical reaction we are balancing when we begin. Um, in general, I like to break it up into three different types. There are combustion reactions, there are acid-base reactions, and there are, well, let's call everything else normal. The reason I have those three types is because it kind of influences how we go about solving the question. In this particular case, it is a combustion reaction. Now, combustion reactions are always going to be between a hydrocarbon, which is this guy right here, and oxygen, and it will always form carbon dioxide and water vapor as your products. And so that's an easy way to identify it. The way that we solve this differently is we are going to first balance everything other than oxygen, put the number of oxygen atoms on the product side over 2, and then multiply through to get rid of our denominator. And that's a really quick and easy way to arrive at the correct solution. So I see that we have 2 carbons here. And so since I have only 1 carbon available on the product side, if I put a 2 right there, that's going to balance my carbons. Not worrying about the oxygen just yet. Looking at hydrogens. On our starting material, we have H6. So I need 6 atoms of hydrogen to appear on the product side. Now, the only place I have hydrogen is right here in my H2O. For every 1 H2O, we have 2 hydrogens. And so if I put a 3 right there, that means that we will have 6 hydrogens on the product side. What I'm going to do from here is tally up all of the oxygens on the product side, accounting for the subscripts on those oxygens and the coefficients in front of each molecule. So for the 2CO2 here, 2 times 2 gives me 4 oxygens. I'm going to add that to the number from the water molecules, 3 times the 1 oxygen there. Remember that the subscripts of 1 are implied. That means I have 3 oxygens from that, which gives me a total of 7 oxygens. I'm going to put the 7 atoms of oxygen over 2. Now, the reason this trick works so well is because we know we need 7 atoms, but we don't actually have atoms of oxygen on the reactant side. We have molecules of O2. So I need 7 oxygen atoms divided by 2. And so to finish this problem off, all I have to do is multiply every coefficient times 2 because that 2 in the numerator will cancel the 2 in the denominator for my oxygens. The result is going to be 2 of the C2H6 plus 7 O2s will yield for me 4 CO2s and 6 H2Os. Make sure that when you're multiplying those coefficients across, you are not touching the subscripts. The subscripts tell you how many atoms of a type are in a particular molecule. That is essential to the identity of each chemical. You cannot change that. All right. The only thing that you're allowed to modify is the coefficients. That is the big numbers that you're putting in front of each individual chemical. Do I have any questions at this point? Okie dokie. We're just going to keep trucking along then. Now I'm doing a little bit of stoichiometry, it looks like. It says consider a 2.663 mole sample of C6H12. How many atoms of hydrogen would be in this sample? So I'm going to start by trying to figure out what type of problem this is. Since it's giving me a unit of moles and a unit of atoms, I think I probably am going to do a dimensional analysis style question. Dimensional analysis isn't just for converting between, miles per hour and kilometers per second, or, those more conventional units. It's actually really useful in chemistry for converting between a quantity of one substance into a quantity of a different substance. I did just see a comment in the chat. I can't actually pause to address the chat. Okay, guys? No worries. Go ahead and speak out loud if you want to interrupt me, and I'd be happy to field your question. No worries. Again, hey,
The question was, is this going to be available to watch later? It's
yes,
on
it
my
is.
YouTube channel.
I will be posting this video to my YouTube channel sometime later tonight. It'll take some time to edit and render it, etc. But sometime after the review is over, you can find it online. Okay, moving on. 2.663 moles of this compound. I like to start by figuring out a good starting point, and in general, it's going to be the only number given to us, 2.663 moles. And now I don't just want to write moles here because you can have a mole of literally anything. It's a quantity, kind of like a dozen of something. And so you have to specify which substance you have that many moles of. In this case, it's going to be C6H12. What I want to do next is figure out how I can convert in between the moles of this substance and moles of some other substance. Anytime you have moles in your dimensional analysis question, that's usually what you're going to do, is find out what other substance you can convert between, because we're looking at different quantities now. It's this quantity versus that quantity, and you can just use a simple ratio. So how many atoms of hydrogen? That's our final product we're looking for here. And so I can derive the ratio just by looking at how many hydrogens are in our starting material. So there are 12 hydrogens for every one C6H12. So I'm going to multiply this by 12H per one C6H12. From here, I like to cancel things as we go through. It just helps to make sure that I'm not tripping myself up. I'm not forgetting anything, not putting things in the numerator when they belong in the denominator instead. Now, I'm not actually going to go through and solve anything until I've gotten the units I want at the end, which is, of course, atoms of hydrogen. At the end here, at this stage, I should have hydrogens, but I have moles too. So I need to find a way to cancel moles to get atoms. This is where Avogadro's number comes into play. It is 6.022 times 10 to the 23rd. I'm going to write it in the format your calculators will show it, 6.022E23. Make sure you're using that E formatting on the exam. I will go through and try and correct for any mistakes that you all make, but it's just easier if you put it in the format the computer expects. So it is that many atoms or molecules per 1 mole. And so I'll put that here, 6.022 E23 atoms per 1 mole. And because I've got moles in the denominator here, moles can cancel in the numerator over there. And checking our work, we just need to make sure all of our units are canceled except for the ones we want, which is, of course, atoms of hydrogen. And then I will finally go ahead and plug it into my calculator and solve. Just in case any of you folks following along have a TI-80 whatever number they're on these days, the way to solve for this is just type in 2.663 times 12 times 6.022. And now what you want to do to find the E on your TI-80 whatever is press the second button, which is in the top left-hand corner, and then the comma button. And on my calculator, that's directly above the number 7. You might see in little letters above the comma the letters EE. That means you're doing 10 to the power of whatever. And then after you see the E appear on the calculator, you just type in the number 23 there. That tells you what the exponent is for scientific notation. And when I hit enter, I get 1.924 e to the 25. And this is the exact format we would want it put on the exam. A note on significant figures. Some of us struggled with those a little bit on the last test. In general, it's not so much of a concern anymore because we're not going to be giving you different measured values to multiply together or anything. You're really just going to be looking at this number and then deciding how many sig figs that has and make sure your final answer has that many sig figs. Because all of the other values I've used are definitional. By definition, there are 12 hydrogens for one C6H12. By definition, Avogadro's number is this. These are considered exact values, and they don't have a role in sig fig calculations. Okay. Any questions at this point? Fabulous. Moving on. Calculate the molarity of a sucrose solution made by dissolving 39.88 grams of sucrose into water, given 682.7 milliliters of solution. The molar mass of sucrose is 342.2 grams per mole. Notice how kind this problem was on the sig figs. Everything has 4 figures in it, so we really don't have to think about it once again. Molarity, I think, really trips students up because they don't really understand what it is. And to be fair, it does sound a lot like moles and molar and all that other mole-ish stuff. Molarity is denoted by a capital M. And what that capital M only means is moles over liters. Exclusively that. I recommend that anytime you see the word molarity or you see a capital M, that you immediately cross that out and write above it moles over liters, or I guess on your scratch paper, you would just write down, make sure it's moles over liters. Whatever value is given to you there, like if they gave us 2.5 moles over liters, it's 2.5 moles over 1 liter. Just some pro tips for not getting that messed up. I've seen students get it backwards lots and lots. Okay. We have quite a few values here. I need to figure out how to put my numbers into an equation that will give me this capital M value. So since I'm looking for moles and liters, I'm essentially going to do 2 different problems here, and I'll solve it together at the end. I need to calculate my number of moles first, and I need to calculate my number of liters. To find moles for a sucrose solution, they gave us 39.88 grams of the sucrose. And they also gave us the molar mass of our sucrose. So I can multiply this by the molar mass of sucrose in order to convert the grams into the moles. Make sure you're always setting your dimensional analysis up so that you're canceling something at every step. Since I have grams in the numerator here, I need grams in the denominator over here. There is no problem with flipping these around back and forth wherever it's convenient for you. It means the same thing. Okay, so that cancels my grams, and that will give me a number of moles, which I can later plug into that molarity equation up top. Now I need to find the number of liters. They gave me milliliters here, 682.7 ml. I can't remember if this conversion is on your formulas sheet or whatever in the exam. I feel like it's one that you all should know. It's probably the most important conversion to go between milli and then the base unit and the base unit and kilo. Like those are the units that most humans use in the rest of the world every single day. Conversions between milli and the base unit, and kilo. And good news, it's very convenient. It's just 1,000. The only tricky part is remembering whether something is smaller or bigger, I suppose. Um, Milliliters are small, kind of like millimeters, right? Milli means a smaller portion of something. Whereas kilo, that's what we measure humans in, how many kilos, or a long distance to run would be several kilometers. And so kilo is big and milli is small. And once you have that sorted out, you can just multiply by the appropriate conversion factor. We're looking for 1 liter on the top, and for every 1 liter, there are 1,000 of those much smaller milliliters. And then we just have to solve. I'll put 39.88 divided by 342.2 into my calculator, and then divide that value by the 0.6827 that we get from doing the liters calculation. And looks like my molarity should be 0.1707 moles over liters. Don't forget your units. Any questions here? Cool. Generally speaking, molarities are small-ish numbers. You're never going to find 1,000 molar of something. It's just not possible because what you're implying is that you've stuffed 1,000 moles into 1 liter, and 1,000 moles is a lot of stuff, and 1 liter is not that much stuff. So it's just not feasible. If you get a value that says like 10 million molar, well, I would go back and check your work. It really helps to kind of ground your answers in your understanding of the physical world because it's just like a reality check you can do for yourself. In lab, you are required to make 414.6 milliliters of a 2.25 molar, there's that capital M again, molar, NaOH solution. How many grams of NaOH should you measure out to make the solution? Let's see. I'm going to take what's a good starting point for this? I need that many milliliters of this thing. So I'm going to start here, 414.6 ml. Full disclosure, literally the first time I've seen any of these problems. I pulled them off of a randomized version of the exam today and didn't think about it aside from that. And so you're watching me solve these in real time and talk through kind of my thought process for this. So we need that many milliliters of this NaOH solution. I know that in 1 liter, we have 1,000 milliliters, and that allows me to cancel this. Once I have liters, I can take my capital M there for molarity, and I'm going to write this as 2.25 moles per 1 liter. And that allows me to cancel the liters. I literally don't know where I'm going with this yet. I'm just canceling units, and I'm probably going to stumble on to the right answer. So I have that many moles of NaOH now. Let's look again at what I'm trying to do here. How many grams, whoops, how many grams of NaOH should I measure out? Well, for grams of NaOH, I know that one thing that links grams and moles is the molar mass of a substance. So I can find the molar mass of sodium hydroxide by pulling up a periodic table. Look. Oh my gosh. Sorry, I got like a drawing tablet that's messing with me. Okay. So sodium 22.9, oxygen roughly 16, and hydrogen roughly 1. Okay. So we're going to add all of those values together since we have one of each. It's the 20. Come on. You know you want to draw a 2 for me. Maybe it doesn't. Ugh. Sorry. I do not know what's wrong. Hmm. Gonna go ahead and unsync my tablet and turn it back on. Okay, that's not the button I pressed. This one? No, no. So sorry for the delay, folks. I'm trying to figure it out. Good old-fashioned refresh, right? Have you turned it off and on again yet? Hey, it was turn it off and on again. Oh man, don't you hate technology? Great. All right. 22.9. Pretend that didn't just phase over there. 22.9 plus 1.00. Man, this thing is really struggling. Okay. Trying this again. Hang on. Ah. Why can't Microsoft make a decent product? Okay. The numbers stay where I put them. Hooray. Plus 1 for the hydrogen, plus roughly 16 for the oxygen. This is all just performative. We're not actually getting graded on this one. Of course, you would use the correct values.
Mr. Ayad,
Hi,
the
Dr. Ayad.
camera
What can I do for
off.
you? Oh, sorry.
Ayad,
Thank you
camera
so much.
off.
Yeah,
Yeah,
sorry about that.
you're good.
Share, share. Perfect. Okay. We can see it now. Yes. Great.
Yes.
Thank you. Thank you. Okay. All I did was add up the numbers for the molar mass, and I got 39.9. And that is, of course, in grams per 1 mole. So then I'm going to multiply this by the 39.9 grams per 1 mole, and that should give me my final answer here. Do I have any questions on the setup of this? Again, the whole intention is we're just trying to cancel units every step of the way. And once I cancel out those moles, well, that is going to give me the correct number of grams of NaOH. Okay. Here we have our first percent yield question.
Could you go back for a second?
Would love to, yeah.
And then you just
Oh yeah, then you just
okay,
you do the numbers thing.
perfect.
Yeah. Any questions? Sorry, I'm getting lazy of the calculator thing. All right. A reaction from lab should theoretically produce that many grams of product if the reaction actually produced. Now, this is really the key phrase here, actually produced. If you see that, what it's telling you is you're doing a percent yield calculation. Now, the percent yield is equal to the actual divided by the theoretical. Actual over theory. It's always going to be actual on top, and that's always going to be the smaller number. Because in the real world, life is hard. Chemistry doesn't work. You get some of your chemicals stuck to your spatula, stuck to your beaker. You spill a little bit on the floor. Some of it turns into the wrong stuff. And so you're always going to end up with a smaller amount in reality than you get in theory. Theory is the perfect case where every molecule converts into the molecule you want it to. And so that's just my way of remembering that the actual goes on top because you're always going to get a percentage lower than 100 here. Of course, for every percentage, you multiply by 100 at the end of the calculation. If you get a percent yield greater than 100% on my exam, then go back and check your work. I think you've done something wrong. In reality, again, things don't work the way we tell you they're going to. Like in your lab classes, you might accidentally get a percent yield higher than 100%. That doesn't mean you're extra good at chemistry. What it means is that you've accidentally included something on the balance that is not your final product, whether it be water or unreacted starting material, or you forgot to zero out the balance, something like that. So yeah, it is possible in a lab class to get a higher than 100% yield, but in our theoretical percent yield calculations, always less than 100. So all we really have to do is figure out where to put these different values. So the theoretical one is going to go on the bottom, and the actual goes on the top. 4.418 grams divided by 78.86 grams times 100 will give me my percent yield. 4.418 divided by 78.86 gives me 0.056, which I then multiply by 100, and I'm getting a 5.602% yield. I am keeping 4 sig figs here because that's how many sig figs were given in the problem. Any questions on the percent yield calculation? All right. Next, we are doing a titration. What volume of that concentration sodium hydroxide is needed to completely titrate that many milliliters of that concentration phosphoric acid according to this equation? Titration is an awful word. I hated it as an undergrad, I hated it as a grad student, and I hate it teaching now too because it just sounds awful and scary. But the good news is we know how to do this problem because we're just doing dimensional analysis. We're given a material, we're converting it to a different material. And that's all we need to worry about. So I'm going to start with these guys, the phosphoric acid, because I don't have as many unknowns here. My unknown is the volume of sodium hydroxide. I know the volume and concentration of my phosphoric acid, so that seems like a convenient starting point. Now you might see the 2.30, the 43 or 483.8 and think, well, which one of those numbers do I put first? I recommend you go with the milliliters. The reason is because that's a lone value. It's just a measurement. While the 2.30 molar, that is a ratio. It is acting as a conversion factor for our dimensional analysis question. So I'm going to start off writing 483.8 ml of, and I'm going to include the phosphoric acid name here, H3PO4, because I want to cancel that at some point during my dimensional analysis problem. The chemical identity needs to be converted into the identity of the other stuff, namely the 3 sodium hydroxides later on. I need this in terms of liters so that I can use my molarity term. Remember, moles over 1 liter. So I'm going to convert this into liters by multiplying this by 1 liter over 1,000 milliliters. Pretend that looks like an M for me. Then I'm going to multiply this by my molarity term, because milliliters has canceled. 2.30 moles over 1 liter. Liters cancels. Now I have moles of the H3PO4, my phosphoric acid. I need to convert that into my other chemical identity, the sodium hydroxide. So you might be looking at this question and saying, but Doc, there are no ratios given here. There's no other conversion factors. How much is it? Well, we're actually using the reaction equation in this case as our conversion factor. So we can check our reaction equation, and we see that for every one of the H3PO4, we need 3 sodium hydroxides in order to make all that other stuff. And so I'm going to write this as a 1:3 ratio, or I suppose I should say 3 NaOH for every 1 phosphoric acid, H3PO4. Now that allows me to cancel out my phosphoric acid. That gives me moles of sodium hydroxide. I need molarity of sodium hydroxide. So I need volume of sodium hydroxide. So I'm going to take my molarity over here. I need moles on the bottom. So I'm going to put the 1 liter on top, and my moles, 6.18 moles on the bottom. And I got that from this value right here. So moles cancels here, and that tells me how many liters of sodium hydroxide. I think in the question on the exam, it probably asks for it in terms of milliliters, not in terms of liters, but the portion I copied doesn't have the milliliter specification, and so we'll just solve for the number of liters here. In my calculator, I type 483.8 divided by 1,000 times 2.3 times 3, and then finally divided by 6.18. And I got 0.54. Would help if I used the correct end of my pencil here. 0.5402 liters of what? The sodium hydroxide, NaOH. Any questions? Yes.
On the exam, will the equation already be balanced when we're doing this one?
I think I believe I was nice. I do believe that it is balanced for you. If I don't specifically say to balance the equation as part of the question, you can assume it is balanced.
Okay,
So,
sounds
so like theoretically, this could be HCl plus NaOH, in which case it would be a 1-to-1 ratio, and you wouldn't see any numbers. In a case where you don't see any numbers, but I don't specifically say balance this equation, you're good. It's 1-to-1.
good. Okay, thank you.
Of course, great question. Anything else, folks? All right, let's keep going. Given the following equation, how many grams of water is produced if 70.80 grams of nitrogen monoxide is produced? Again, sounds scary, but I'm just going to be thinking about dimensional analysis. I'm just going to write some numbers down. I see 70.80 grams. It's a really good place to start. 70.80 G. And I want to make sure I include the chemical identity here because they gave us a reaction equation. They're asking for mole or grams of a different substance. And so I'm going to need to include my chemical identity so I can cancel it out at some point in this reaction. So I'm going to write NO, nitrogen monoxide there. And I'm going to multiply this by something. There's not a lot of other information given here, or at least no other numbers given and no other conversion factors. So we have to do a little bit of digging to figure out what conversion factors are necessary. I like to say that moles is kind of the grand unifier in chemistry. It's where we always want to aim for in our problems so that we can convert between moles of one substance and moles of a different substance. You really can't compare grams to grams of anything. You have to go to moles first. And so if you're stuck in a problem like this, go to moles. I see grams of NO. I want moles of NO. So I need the molar mass of my nitrogen monoxide. So a periodic table would tell you that nitrogen weighs roughly 14 and oxygen is roughly 16. I'm going to add these two values together and get 30. Make sure you use the actual values from your periodic tables on the exam. I'm just trying to save a little bit of time so I don't have to pull it up and accidentally break my notepad again. Okay, so we have 1 mole there and 30 grams down there. Grams cancels with grams. I have moles of nitrogen monoxide now. Once you have moles of a substance, this is where you convert into the other substance. What other substance am I looking for? H2O, good old-fashioned water. And so the ratio between water and nitrogen monoxide is contained in this balanced chemical equation up here. I see that we have 4 NOs for every 6 H2Os. You don't need to worry about whether things are on reactant side or product side. The ratio is true regardless of which side of the equation you find the chemical identity. So I just need to make sure that I set up this 4-to-6 ratio such that I'm canceling the NOs, which means I'll put 6H2O on the top and 4NO on the bottom. Now, those of you in the class that are math whizzes will quickly think to yourselves, oh, how simple. This is clearly just 3/2. Yes, good job. But I'd argue that that's not exactly a useful calculation to do in your head and that you would be better served writing it down as 6/4. The reason is because mathematically they are identical statements and chemically they are not identical. Because this specifically tells us that the 6 comes from that balanced chemical equation. The 4 is the number of NOs necessary to balance those 6 H2Os out. And when you're going back and checking your work, or more importantly, when I'm checking your work, traceability of the information is really important. So I would leave it as 6/4 if I were you. I'm now going to multiply this by what? Well, I've canceled out my nitrogen monoxide. I have moles of water. And what am I looking for? Of course, grams of water. To find the grams from this equation, I need, once again, the molar mass of my substance, in this case, H2O. Hydrogen is roughly 1, and I have 2 of those, and oxygen is roughly 16, and I have just 1 of those. And so when I add all that together, we're going to get roughly 18 grams per mole here. In this case, I'm going to put the 18G on top and the 1 mole on the bottom. Moles cancels with moles, and this is going to give me the final value here. I assume somebody gets something out of me typing these numbers into my own calculator, so I'm going to keep doing that, I guess. 70.80 divided by 30. And then I'm going to do times 6, and then I'm going to do divided by 4. The order of operations does not matter here because multiplication and division are ranked the same in order of priority, that is. And so my final value here is 63.72 grams of what? Of course, H2O, the only substance we haven't crossed out. Do I have any questions? Well, I hope you all are having as much fun as I am. Let's keep rolling. A sample of hydrocarbon is found to contain 7.92 grams of carbon and 0.665 grams of hydrogen. What is the empirical formula for this compound? So to solve this question, we really have to ask ourselves what an empirical formula is. The empirical formula is the lowest whole number ratio of each element to all the other elements in a particular compound. And it can be expressed as, in this case, CXHY, where both X and Y are integers. The reason they have to be integers is because you can't have a half of an atom. Half of an atom would have a different number of protons and electrons and would therefore be a different atom. Remember, the identity of each atom is dependent on the number of protons. And so it's kind of the lowest unreducible ratio of these things. In order to figure out the empirical formula from a quantity of grams, I of course need to put this into some term that is irrespective of the mass of each element. And of course, that is going to be moles for us. Again, when in doubt, turn it into moles, see what happens. So I'm going to take my 7.92 grams of carbon and multiply it by the molar mass of carbon. I want moles on top here so that I can plug my molar value into my X up here eventually. And the molar mass from our periodic table is 12.01 grams. Grams canceled with grams, and that'll give me a quantity of moles that I'll calculate in a second. I'm going to do the same treatment for my hydrogens. 0.665. 0.665 grams of hydrogen times 1 mole per 1.008 grams, which would also make grams cancel with grams and give me the moles of hydrogen present. I'll plug it into my calculator real quick. 7.92 divided by 12.01 gives me 0.659. And I guess that's all the sig figs I really need here because we just started with 3. And of course, that is moles of C. I do the same thing for the hydrogen next, 0.665 divided by 1.008, and I get 0.65. Well, I guess if I worry about the sig figs, that means it would actually be 60, because I would round up in this particular case, moles of hydrogen. Okay. Now you might be looking at that and saying, Dr. Ayad, those are definitely not whole numbers. That's okay, because we were given kind of arbitrary values there. We're just trying to find what the ratio would be, the lowest whole number ratio. So I can plug those values in for X and Y respectively here. So I'll do C of 0.659 and H 0.660. And then I'm going to divide by the smallest one of those numbers. The reason I choose to divide by the smallest one of those numbers is because that'll always make the smallest whole number equal to exactly 1, which is a good starting point in finding the lowest whole number ratio. Now, it won't always have a 1 as part of your lowest whole number ratio, but it's usually easier to see the factors that way. You can usually see, oh, if one of them is 1 and the other one is 1.5, well, you obviously have to multiply both of them by 2 to get 2 and then 3. So I'm going to divide both of these by the smaller number, 0.659, and divided by 0.659. And that's going to give me C1H1 point like 001-ish. I didn't actually plug it in my calculator. I just know it's going to be around there. You do not need to multiply this by 1,000 in order to get the lowest whole number ratio. All right. These are measurements. Somebody did an experiment, calculated to just 3 sig figs, not very many sig figs, not really certain of that measurement. These were the two quantities of those substances. So any value on the decimal end, that is, I would say less than 0.2 or 0.3, you can ignore. And we'll just say that this is a C1H1 as our empirical formula. Any questions here? Cool. Oh, thank God, a break from the math for a second. What is the oxidation number on sulfur in the following compound, H2SO4? If you Google it, and you look for what are the rules for oxidation numbers, you're going to find a lot of rules and a lot of gray area. But really, I just care about 3 things here, okay? Hydrogen is going to be equal to a +1. Oxygen is going to be equal to a -2. And we'll say the halogens will pretty much always be equal to -1. And yes, there are exceptions to literally every one of those 3 quote-unquote rules. But for any of the questions I would give you on the exam, this is what you need to know. So how do we use these rules to solve for the oxidation number of some other element? Well, the other element will always be the only unknown in these types of questions. All right. You will always have given to you hydrogens, oxygens, or some of the halogens so that you can set up a basic algebraic expression to solve for S. So what I like to do is I rewrite everything somewhere that I have lots of room to play with the values. H2S, and we'll put O4 here. So I like to place the expected oxidation value for individual elements above their respective element. What do I mean by that? Well, H over here, we said was +1. And so I'm going to put a +1 above the H. Oxygen is a -2 here. So I'm going to put a -2 above the oxygen. Sulfur isn't one of these 3 things. And so it is our unknown. And just like in math, we're going to use the letter X to specify an unknown. How many hydrogens do I have? Well, I have 2 hydrogens here. So I'm going to take the +1, multiply it by the 2 for a total of a +2 oxidation number there. I'm going to add to that X times the number of sulfurs. There's just 1 sulfur, so I'm adding 1X here. For the oxygens, I have -2, and then there's 4 of those. So there's a whole lot of negative oxidation value here. -2 times 4 gives me a -8. You could also write this as +-8, means the same thing. You do you. Now, like any good algebraic expression, it needs to be equal to something. What are we going to set it equal to? Well, oxidation number and charge of a molecule are intricately linked to one another. The oxidation numbers of all the individual atoms summed up should equal the charge. What is the charge of H2SO4? It doesn't say, right? Anytime that it doesn't say the charge, we assume it is zero. Just like ones, they're implied, right? It would suck if you had to write zero literally every time a molecule wasn't charged, because that's kind of their default state, is to be uncharged. And so I'm going to set this whole equation equal to the charge, which was not listed, and so it is zero. Now to solve, I just have to rearrange. I can add 8 to both sides, and I can subtract 2 from both sides. When I do that, I end up with x is equal to a positive 6, and that is the oxidation number for my sulfur. You can always check your work when doing these types of questions just by plugging in that value you got for x into the above equation and making sure it actually does equal 0 and you didn't make some kind of a transcription error. Any questions? In the home stretch now. Consider the following reaction. Identify what main category of reaction it is. If possible, further categorize it into other relevant types of reaction. So this is just me showing you what type of question this is. Wasn't able to copy all of the different multiple choice options there. You have like a select all that apply here. Let's talk about what this one might be. So there are several major types of reactions. There were double displacement, single displacement, combustion, acid base. And when you're solving any of those, I think that's just helpful to like do flashcards with the definitions and look for characteristic reactants or products. In particular, if you see a reaction equation where you would name one of the compounds with the word acid, in this case it is sulfuric acid, pretty good odds it's an acid-base reaction. And so I'll just mark down acid-base here for this one. Now, that doesn't mean it's the only type of reaction here. You can also potentially have an acid-base reaction that causes precipitation to occur, in which case you would also mark down precipitation. In this case, I wouldn't say that it's precipitation because we have potassium sulfate, and all of the potassium salts are listed as being soluble. What else could it be? Well, we had one that was called double displacement or double replacement, in which one of the ions essentially swaps with one of the other ions from the other molecule. And in this case, it does kind of look like the hydrogens swap places with the potassiums. So I would say this is also a double displacement. One other really characteristic type of reaction that you could find would be like a combustion of a hydrocarbon. So earlier we saw 2C2H6 plus 7O2 yields, I think it was 4 CO2 and 6 H2Os. This would be a good example of a combustion reaction. You can identify combustion reactions pretty quickly because they're always going to produce exclusively CO2 and H2O. If carbon dioxide and water are the only two things you form, it's a combustion reaction. You should also be looking at this part right here. See if you have a hydrocarbon. Hydrocarbons do as their name says. They are hydrogen and carbon. They can have a little oxygen thrown into, sometimes a little nitrogen, but if you see a bunch of carbon and a bunch of hydrogen, assume it's a hydrocarbon and assume it burns really well. So this would be a good example of a combustion reaction. Now, this is another type of reaction too, and it might be hard to see at first until you get really familiar with oxidation rules. So on the last slide, I showed you all the 3 most important numbers you have to memorize. I should mention one other thing, though, that pure elements have an oxidation number of 0. If it's just oxygen, just nitrogen, just carbon, just whatever, then its oxidation number is 0. So we start with something that has an oxidation number of 0. Wish my 0 looked less like a backward 6. But you get the idea, right? So if the oxygen is 0 here, but over here it's part of a compound and therefore is -2, and similarly over here is -2. Well, we've changed the oxidation number of one of our molecules. Anytime you change the oxidation number, it is necessarily a redox reaction. That's just another one of the archetypes you could be looking for. Any questions here? Okay. How many milliliters of a 7.01 molar HCl solution would it take to make that many milliliters of that molarity solution? This one's a little tricky. Not that it's hard to solve, but just that it kind of goes against the trend of just turn everything into moles. You can technically do that here, but it's actually way more work to do that. Instead, we like to use a simpler equation, which I call the dilution equation. When do you use the dilution equation? Well, anytime it says to you how much of this concentration solution do you need for this concentration solution. It takes the basic form of concentration times volume is equal to another concentration times another volume. We can be more specific with our concentrations and volumes here, and this becomes molarity as one of our concentrations. And for the volume here, it's very convenient. We have milliliters there and milliliters there, so I can just make this milliliters here is equal to concentration 2. Of course, these are both 1 and 1, and this is going to be molarity 2 and milliliters 2. So now I just need to plug in for these values. It doesn't matter really which one of these you decide is M1 or M2. What does matter, though, is that you keep each respective milliliters with its concentration. So we have 250 milliliters of 2.10 molar solution. So I'm going to put both of those as number 1. So my molarity, 2.10 molar times my milliliters, 250 ml, is going to be equal to this concentration, 7.01 molar, times some other number of milliliters, which I'll just call X milliliters. Notice that because I have molar and milliliter on both sides, the units are going to cancel out in a really convenient way. So you don't have to fumble around with converting between liters and milliliters and all that jazz. So to solve this, I'm going to do 2.10 times 250 gives me 525, and I'll mess with the units later, is equal to 7.01 x, and I just divide by 7.01 on both sides of my equation, and that's going to give me x equal to 74 point, and we're looking for 3 sig figs here, so we'll call it 9 milliliters. Let's reality check this, because this is a real thing. You can do this. You can mix a concentrated thing with more water to make a less concentrated thing. So let's think about our value in that context, right? Imagine you have like concentrated Gatorade solution and you're trying to water it down some. You're going to use a small amount of that Gatorade solution to make a larger volume of the less concentrated Gatorade. That's effectively what we've done here, right? We took 75 milliliters of a concentrated solution to make 250 milliliters of a less concentrated solution. So I definitely think that our value is within the realm of possibility. You want to make sure that you don't have any negative values here. That is physically impossible. We don't have antimatter, no matter what the physicists are trying to tell you. You want to make sure it's not bigger than your diluted value, right? You're not going to dilute something and then end up with less stuff. By its very nature, you should end up with more stuff after you do the dilution. Just some things to check for. Any questions? Okay. I have saved the best for last. This is the big one. It asks us to do pretty much everything, right? We got to make sure the equation is balanced. We got to turn one substance into another substance. And they've specified the actual amounts of each that we have. You want to look out for the keywords limiting reagent in these types of problems because that's going to tell you, hey, this is not present in an equimolar amount. We are given limited quantities of each, and we're probably going to have a little extra of one rather than the other. To make sense of this in a more like everyday example, I like to use the grilled cheese analogy, right? Let's say you got a bunch of guests over, you want to make a bunch of grilled cheese, right? You got a pack of Kraft singles that has 11 slices of cheese left in it, and you've got half a loaf of bread. Let's say that you have 13 slices of bread, right? Every slice of cheese needs 2 slices of bread in order to make one grilled cheese. Well, after some simple math, you would find you have way more cheese than you do bread, accounting for those ratios. You are limited by the amount of bread you have, and you have an excess of cheese. That's effectively what's happening here, just with scarier sounding things like magnesium and fluorine. So, how do we account for the limiting reagent? We effectively need to do two different calculations and figure out which substance runs out first. Whichever substance runs out first is necessarily the limiting reagent, and that's what happens in reality. I would like more grilled cheese, but I am limited by the amount of bread I have. And so the amount of grilled cheese I can actually make depends only on the amount of bread. I can have an infinite amount of cheese, and it will not make me more grilled cheese sandwiches. So, silly analogy concluded. Let's get into the problem. Is this equation balanced? Well, let's check. One magnesium, one magnesium. So far, so good. One F2, one F2. Great. It's already balanced for us. We don't need to worry about that. The reaction starts with that many grams of magnesium, that many grams of fluorine. This is how I'm going to set up my two parallel dimensional analysis problems. 24.19 grams mg. And then on this other line, 83.35 grams of F2. And I'll be multiplying both of these by some value to turn it into moles. We always want to go to moles so that we can convert into a different material. The other material in this case we're looking for is the grams of magnesium fluoride. That's this product right here. And so I'm going to be converting both of them into the same product so that I can compare which one runs out first, which one makes less stuff. The molar mass of magnesium, let's see here. Okay. Magnesium is 24.305, and the fluorine is 19. We'll use it as 24.3 grams and 1 mole on the top. And the F2 is 1 mole and not really 19, right? This says 18.99. We assumed it was 19, but that's for one fluorine. Don't fall into this trap. Just because it's a pure element, it's still F2. There's two of those 19s stuck together for a total of, let's call it 38. Grams cancels with grams in both cases. I like to do these literally in parallel because it's just easiest to think about each step one at a time. I've got moles of each substance. Once you have moles, you can convert into the product. Luckily, it's all 1-to-1 ratios, but I do think it's worthwhile to draw out the steps anyway. 1 mgF2 per 1 mg, and we have 1 magnesium fluoride for every 1 fluorine gas. Now what I need to do is I need to cross out my stuff. I have moles of magnesium fluoride. We're looking for grams of magnesium fluoride. You can technically find which one is the limiting reagent at this stage just by looking at the moles, but since we need grams anyway, why not calculate it? So luckily the reaction math is pretty easy here. We're just adding the molar mass of magnesium to the molar mass of the fluorine. I pointed to the wrong thing on the computer, but you use the molar masses from your periodic table. 24.3 for the magnesium plus 38 from the fluorine gives me 62.3 grams on the top and 1 mole on the bottom. And that's going to be the same for this bottom equation because this is the molar mass for our magnesium fluoride. We cancel our units, and what we're left with is grams of magnesium fluoride in both cases. So that allows me to really compare apples to apples here. I'll go ahead and solve now. 24.19 divided by 24.3 times 62.3 gives me 62.0 grams of mg F2. I am including the 0.0 there because it is a significant figure. I guess I should probably include more actually, shouldn't I? Yeah, we were using 4 sig figs in the problem, so it's actually 0.2. And then for the bottom equation, 83.35 divided by 38 times 62.2 gives me 136.4 grams of mgF2. Now, certainly I would prefer if I could get twice as much stuff, but that's just not the reality of the situation. I am limited to producing this much stuff. This is, as a result, my theoretical yield. And your theoretical yield comes from whichever material was your limiting reagent. In this case, the limiting reagent is magnesium. And that's it. That is the worst question on the test. I guarantee it. Or at least it's the one that takes me the longest to solve. I find the most conceptually challenging. And I think most of you would agree. Do I have any questions?
Yes. Do you have a way that I could easily remember what's insoluble? Insoluble?
Good news. You're going to get a table on the exam. It's going to look very similar to the ones from your homework. And so you just need to be able to follow the solubility table. I can't even remember all of the solubility rules, and I've been doing this a really, really long time. And so as long as you know how to read the table, you should be good.
Oh, okay. And other question it well not question, but I didn't see the assignment to submit the my work after I'm done with the test.
So sorry about that. But you still don't see it? Because
No.
I think it wasn't published earlier today, but it should be published now. I'll go ahead and double check to make sure it does show up. It should be right underneath the exam in this week's module. There's
Mm,
always a chance that I've messed that up, though. I will double check later.
Let me look right now too. I'll let you know.
Okay, thank you so much. Other questions?
Yes,
Okay,
there. I see it.
great. Thanks so much. Anything else, folks? I am going to call it a night if you don't have any questions. I do really appreciate everybody showing up and interacting with me for this. I appreciate you guys working hard, studying for this test. Chemistry is fun for a very select few of us, and there's a chance I am alone in that on this Zoom call. So I do extra appreciate the effort you all put into learning this subject. Thank you for your time. If you have any questions after this, please feel free to shoot me an email. I've got Zoom office hours tomorrow from 4 to 5. That's another good time to reach me. And again, Thursday at 9 a.m. Um, it's been a pleasure, and I will post this shortly. Thank you so much. Have a great night.
Thank you.
Thank you.
Yeah, of course, guys.
Thank you.
You're welcome.